Kagglers. Welcome to the live stream. I'm just checking my levels and I'm doing my traditional waffling until the stream catches up with me, which always takes a bit. Hi. I mentioned last time when we were wrapping up the reading stream, the last paper we read, that I might just do an executive decision and decide that we were going to read EfficientNet, and clearly I have done that. And the reason that I've done that is, so if this is a reading group, then the way that, at least the reading groups that I've interacted with in university settings have been, is that people can suggest papers, but every so often whoever's leading the reading group, which is usually a professor, usually it's for their lab, will be like, nah, this one's important, we gotta read this one. And this is me being like, nah, this one's important, we gotta read this one. So EfficientNet has been around for... Nope. Oh, can't handle that. Turning off the autofocus. Give me just 1 second. So EfficientNet has been around for a little bit. And apply. Okay, I'm done. And I want to say it was released in early 2019, late 2018, and then it was published at ICML 2018. So the last paper we read had not been published, it was under review, and this one has been published. Layla says, EfficientNet finally. I know, it's been so long. I had it in the poll for like 4 months maybe. And you'll see says, the BigQuery teacher, the best. Oh, thank you, you're the best. So I will say that this is about convolutional neural networks, which I don't know as well as recurrent neural networks, but I have been promised that it is very light on the computer vision, so hopefully we'll get through this no problem. All right, let's get started. EfficientNet, Rethinking Model Scaling for Convolutional Neural Networks, and it's by Minting Tan and Kaggle. I actually have an interview with Kaggle on the channel from a while ago, if you want to go back and check that out. It's a coffee chat. Zoom in so y'all can see a little bit better. All right, abstract. Convolutional neural networks, ConvNets. Oh, usually I would abbreviate that CNN, but ConvNets is how we're abbreviating it here, are commonly developed at a fixed resource budget and then scaled up for better accuracy if more resources are available. That sort of jives with my intuition. So you train like a small one, or like the biggest one you can get away with, and then if it starts to work really well, you can make the case that you should train it more, or train a bigger one or something like that. In this paper, we systematically study model scaling and identify that carefully balancing network depth, so number of layers, width, number, like the dimensions, there we go, the dimensions of the network, and resolution. I think that's the size of the convolution layer. I think it's whether it's bigger or smaller. Hopefully they'll talk about that. Can lead to better performance. Based on this observation, we propose a new scaling method that uniformly scales all dimension of depth, width, resolution using a simple yet highly effective compound coefficient. Okay, so like a zoom button, I guess, for network architecture. We demonstrate the effectiveness of this method on scaling up mobile nets and ResNet. Oh, I know this is, I want to say this is a TensorFlow model that works for embedded systems very well, and ResNet, I don't know. I've heard these words, I just don't know what they are in any depth. Hello to everybody. Kali says, what is the Kaggle reading group? Is there any particular schedule? And where can I find out more about this group? So we read papers. In this case, we're just starting out with the EfficientNet paper, and I just read them in real time, and people ask questions and offer additional supporting information, and we all learn together. And they are every Wednesday at 9 a.m. Pacific time, which is this time. Yeah, good question. To go even further, we use neural architecture search to design a new baseline network and scale it up to obtain a family of models called EfficientNets, which achieve much better accuracy and efficiency than previous convnets, convolutional neural networks. So Kwakla's main research area is this neural architecture search, so finding families of architectures that work particularly well for specific problems. And if you have spent much time in learning about deep learning and the current research, there's sort of a like if you're doing regression on a data set, there's sort of a principles that you can use to be like, given this is the best regression model, right? But we don't really have that for deep learning and neural networks. We sort of have general classes of problems that there's empirical evidence that a specific family of models tend to work better for. So recurrent neural networks tend to work better for sequential data because that's what they're designed to handle. But there's no like principled, this is the best model for this thing. And the sort of hope of the neural architecture search literature is that we can develop models and discover families of models that are particularly good for particular problems. That's very similar to the paper that we read before last with David Ha was one of the authors, and I want to say Ian somebody was the other author, on developing neural architecture search, where you don't train the weights, you train the architecture. Anyway, that's an aside. So they have a new family of models. In particular, our EfficientNet B7 achieves state-of-the-art 84.4 top 1/97.1 top 5 accuracy on Imagenet. So I believe they're saying that they identify so Imagenet is like a labeled image data set that has like things in it, right? Like it's photos with like giraffes and zebras and cars and whatnot. And I think what they're saying is that 84% of the time, the top object that they guess is correct, and 97% of the time, they correctly guess the top object in their top 5 candidates, is what I'm getting from that. On Imagenet, so it's doing really, really well, very accurate, well, being 8.4 times smaller and 6.1 times faster on inference than the best existing convolutional network. So it's smaller, which means when you're going through and you're guessing things using the model, it does it much faster. Excuse me. Our EfficientNets also transfer well and achieve state-of-the-art accuracy on CFAIR 100, that's another image set, I don't know what's in that one, flowers, and 3 other transfer learning data sets with an order of magnitude fewer parameters. So these are small models that it's very fast to actually use once they're trained, and they're doing very well. That's the idea. Ravi says, you are NLP, but you're reading CNNs, it's used in vision. Yeah, definitely. I have much more depth of knowledge in natural language processing, but I am interested in sort of machine learning methods in general, and convolutional neural networks are an important part of those. So, and again, this is an important paper. I would say that it's, oh my gosh, sorry. I'm allergic to something. Don't know what it is, but it's out there. I would say that this is a very important paper for machine learning in general, and the fact that it is on image data does not make it less relevant. All right, introduction. Oh, and affiliations, both authors are from the Google Brain research team in Mountain View. And then it was published at ICML 2019, that was in Long Beach. Introduction. Scaling up convnets is widely used to achieve better accuracy. So I think I mentioned this before. In general, the sort of trend in machine learning is bigger data, bigger model, trains for longer, better results. That's sort of the overwhelming trend of the last like 10, 15 years. Master Chief says, allergic to CNN. Hopefully not. That would be unfortunate. Pujitha says, is there a specific pre-trained model that's best for speech emotion recognition task? I don't know. I'm not that familiar with the literature. All right. For example, ResNet et al. 2016 can be scaled up from ResNet 18 to ResNet 200 by using more layers. So adding, additional depth to the model. Recently, GPipe, Huang et al. 2018, achieved 84.3% Imagenet top 1 accuracy by scaling up a baseline model 4 times larger. However, the process of scaling up convnets has never been well understood, and there are currently many ways to do it. The common way to scale up convnets is by their depth, so adding more layers more layers in your neural network, or width, making each layer wider. Another less common but increasingly popular method is to scale up models by image resolution. Oh, so you're looking at bigger images. Yeah, I think that's the thing that they're doing here. Anarchy says, can you teach me how to find the best model? I mean, see the entire field of machine learning research. No, not for every problem. Anyone who could would be an extremely impressive, well-rounded researcher. All right. Another less blah, blah. In previous work, it's common to scale only one of the 3 dimensions, depth, width, and image size. Though it is possible, so like the thing where I was like the size of the convolution is changed, that's nothing. I just made that up. In previous work, it's common to scale only one of the 3 dimensions, depth, width, and image size. Though it is possible to scale 2 or 3 dimensions arbitrarily, arbitrary scaling requires tedious manual tuning and still often yields suboptimal accuracy and efficiency. So if you just try to maybe I'll make it a little bit wider and then a lot deeper, or maybe I'll take it a lot deeper and a little bit wider, I don't know what's going to happen. That sort of guess and test takes a while, and you have to do it by hand, hence manual tuning, and you don't know that you're going to get the best or the most accurate or the most easy to use model. Because the bigger, like a bigger neural network is, you have your input, you're going through to your output, the longer it's going to take to go through. So smaller networks generally run a little bit faster. Although it's like, depending on what you're doing, it may still be pretty fast. So in this paper, we want to study and rethink the process of scaling up convnets. In particular, we investigate the central question. Is there a principled method to scale up convnets that can achieve better accuracy and efficiency? Our empirical study shows that it is critical to balance all dimensions of network width, depth, resolution, and surprisingly, such balance can be achieved by simply scaling each of them with a constant ratio. Okay, so image is 20% bigger, network's 20% wider, 20% more layers, for example. Based on this observation, we propose a simple yet effective compound scaling method. Unlike conventional practice that arbitrarily scales these factors, our method uniformly scales network width, depth, and resolution with a set of fixed scaling coefficients. For example, if we want to use 2 to the nth times more computational resources, then we can simply increase the network depth by alpha to the nth, width by beta to the nth, and image size by gamma to the nth. I'm pretty sure that's gamma. Where alpha, beta, gamma are constant coefficients determined by a small grid search on the original small model. Figure 2 illustrates the difference between our scaling method and conventional scaling methods. Okay, so you have a constant, and each of your scaling parameters is raised to that constant, and these are learned based on the smaller initial model. Ayush says, EfficientNets performed well in Aptos 2019 Blindness Detection Challenge. That closed pretty recently. It's a Kaggle competition. What was observed that increasing the image size and model complexity B0 to B7 gave better results. Oh, interesting. I've also heard people talking about B6 being particularly good for things. Again, I haven't read the paper, so I was like, these sound like vitamins, but I believe you that they're models. And now I'm excited to know more about the models. Okay, so we've got here our example ways of scaling. So here we have model scaling. A is our baseline network example. So here's the baseline. B through D, these three here, are conventional scaling that only increases one dimension of network width, depth, or resolution. E is our proposed compound scaling method that uniformly scales all three dimensions with a fixed ratio. So if you have your model, let me zoom in here, so it's got 5 layers and they're like 1 inch across. I don't know how to like talk about width in words. So you have 5 layers, and then the first layer is the resolution height by width times 2, and then this is layer sub I. I don't know why that's important. Do we refer to sub I again? We don't. Okay, so just and then we have just like an intermediate layer. And then the output is the channels for like classification, I'm guessing. So one thing that people will do is they'll make the model wider. So this looks like each layer is twice as wide. And then another thing that people do is that they make the model deeper. So for each input component, they use 2 of them at a time. If you remember for transformers uses this, or at least the original Vaswani paper uses this this practice where there's, I think, like 8 per stack of the things, the components. I forget the thing that they're called, but there are multiple stacks of them. And then resolution scaling, you make the height and width of the input image bigger, but you don't add a separate module and you don't make these wider. And then the method that they're proposing, they make the it looks like it's about 1.5 times as wide. So each layer is about 1.5 times as wide. The input has a higher resolution, and they're including, it looks like each section is 1.5 times as deep as well. So the bigger image, wider layers, and then more of them, but not as many as someone who's going all in on making the model deeper, and not as wide as someone who's going all in on making the model wider, and the image isn't as big as someone who's going all in on making the image bigger. So it's sort of a balance between these things. Ryan says the width is the number of channels/filters, so the size of the network here. So instead of doing 16 3x3 kernels, they might do 32 3x3 kernels. Okay. I know some of those words. All right, where were we? And then the 1.5 here would be learned, and it would be learned separately for the size of the image, the width of the model, and then the depth of the model. Intuitively, the compound scaling method makes sense because if the input image is bigger, then the network needs more layers to increase the receptive field and more channels to capture fine-grained patterns on the bigger image. In fact, previous theoretical, Raku et al. 2017 and Liu et al. 2018, and empirical results, Zagoryuko and Komodakis, I'm guessing, 2016, both show that there exists certain relationship between network width and depth, but to the best of our knowledge, we are the first to empirically quantify the relationship among all 3 dimensions of network width, depth, and resolution. We demonstrate that our scaling methods work well on existing mobile nets, Howard et al. 2017, Sandler et al. 2018, and ResNet et al. 2016. Notably, the effectiveness of model scaling heavily depends on the baseline network. To go even further, we use neural architecture search, Zoff and Lee 2017 and Tan et al. 2019, to develop a new baseline network and scale it up to obtain a family of models called EfficientNet. Okay, so the scaling isn't going to work equally well on every single network you put into it. You need to have a good baseline network first. And that, I think, makes sense intuitively. If you have a network that's just like an awful fit for your specific problem, then making it bigger isn't necessarily going to help. So they're also looking at a different baseline network architecture that they're finding through neural architecture search. Neural architecture search is where you use machine learning to find the best architecture for your problem. It's much more expensive than regular regular training a neural network, because you have to train multiple ones and see which one's good, and then keep training, etc. We talked about this in the interview. I don't want to go too deep into it. All right. Figure 1 summarizes the Imagenet performance, where our EfficientNet significantly outperform other convnets. In particular, our EfficientNet B7 surpasses the best existing G-pipe accuracy, Huang et al. 2018, but using 8.4 times fewer parameters and running 6 times faster on inference. So it isn't necessarily going to train faster, although I imagine it would because it's smaller. But it is much faster to get the answers out from the model, or at least the model's guesses. I shouldn't say the answers. Arif says they are keeping something in the model fixed here while scaling. What is that? It's not number of layers, right? I.e., what are the separate modules in different colors in figure 2? I think each of these is a convolution. Someone who's more familiar with CNNs might be able to jump in here. So I think what they're keeping the same is sort of the flavor of each layer of the model, and what they're changing is just the size of everything. Is my guess. Feel free to jump in the chat if you have more information. Compared to widely used ResNet et al. 2016, our EfficientNet B4 improves the top 1 accuracy from 76.3% of ResNet 50 to 82.6% with similar flops. Don't know what flops are. Besides Imagenet, EfficientNets also transfer well and achieve state-of-the-art accuracy on 5 out of 8 widely used datasets, while reducing parameters by up to 21 times compared to existing convnets. So they're saying that because this is an architecture that they've sort of discovered, they're saying that it transfers really well to work on different types of data sets and different questions, and that it's working equally well across a wide variety of things, which is good to know, because one of the things that you can imagine might happen during neural architecture search is that you might find an architecture that works really well for like your specific exact problem, but not generally well. Scroll. 2, related work. Finally, related work at the beginning of the paper, where it belongs. Oh, thank you. Sanjaya says flops is floating point operations per second. And Frank is also hopping in with that. Thank you. That makes a lot of sense. So the number of calculations you need to do per second. Okay, so they're doing there's a similar rate of calculations, but they have increased their accuracy. So they're more efficient. Hence the name. All right. Convnet accuracy. Since AlexNet, Krzyzewski et al. 2012 run the 2012 Imagenet competition, convnets have become increasingly more accurate by going bigger. Also true in NLP in general. Well, the 2014 Imagenet winner, GoogleNet, why can't people just use IPA? I know why. Szegedi et al. 2015 achieved 74.8% top 1 accuracy with about 6.8 million parameters. The 2017 Imagenet winner, Hu et al. 2018 achieves 82.7% top 1 accuracy with 145 million parameters. That's so big. Ryan says, might be useful to look up Sobel filters if interested in understanding a bit more about CNNs. Imagine your base 224 by 224 image and then passing a little decoder lens over it and getting a new view. So sort of like some people have found that the best decoder lens is for certain things like edge detections, but CNNs are automatically finding these decoder lenses. Okay, interesting. Because the decoder lenses are going to intentionally introduce distortion, and then what CNNs are doing is that they are finding the type of distortion that's most useful for the task at hand, is what I'm understanding from Ryan's explanation. All right, so we were. I like related works because it's like a little story time where you get to learn what people have been up to. So we're working on this data set. The models are getting significantly bigger. So we started out with 6.8 million parameters and then 145 million parameters, but also so does the accuracy. So that got us like an additional almost 10% boost in accuracy. Recently, GPipe, Huang et al. 2018, further pushes state-of-the-art Imagenet top 1 validation accuracy to 84.3% using 557 million parameters. In here is the point at which I probably, let's be honest, like here is about the point where I would have given up. So that was 6. That was 145. I'm trying to think about how many times bigger it is, and I'm going to drink some coffee instead of doing the math. But this jump in size got us a really large jump in accuracy. This jump in size got us a much smaller jump in accuracy. GPipe. It is so big that it can only be trained with a specialized pipeline parallelism library by partitioning the network and spreading each part to a different accelerator. Oof. While these models are mainly designed for Imagenet, recent studies have shown better Imagenet models also perform better on a variety of transfer learning datasets, Kornblith et al. 2019, and other computer vision tasks such as object detection, He et al. 2016, and Tan et al. 2019. I know one of the problems in that people working in computer vision are worried about is the degree to which the field is overfitting to Imagenet, because they've got this big data set that everyone's working on, and it's got, its own statistical anomalies. Like, I know there's like a lot of drafts in it. That's why I keep saying drafts. Or most pictures of people tend to be people wearing seatbelts. So there's like a weird, often weirdnesses in the seatbelt labels. But there is evidence that they're not just like Imagenet models, they are a little bit more generalizable, which is good. Although higher accuracy is critical for many applications, we have already hit the hardware memory limit, and thus further accuracy gain needs better efficiency. Ryan says, when I say 16 3x3 kernels, I mean they're having CNN find 16 different decoder lenses to view the image through. Okay, that makes sense. So it's like, I know this is a poor analogy, but it's like the eyes of a spider, and then each kernel would be a spider eye that's doing some sort of processing to help better understand it's not always going to be a scene, not everything's doing scene recognition, but Layla says, what are transfer learning datasets? Ooh, good question. Let's find out. Kornblith, and we are right now on page 2. Let's go down. Boop. A, B, C, D, E, F, G, H, I, J, Kornblith. Do better ImageNet models transfer better? So I think what they mean is that they are trying to transfer the models to different data sets, and they're doing that using transfer learning, which is where you take a model that's been trained and then you modify it slightly to work better for a separate task. So if you happen to catch any of the glue papers we've talked about, glue is an NLP data set that has many different tasks in it, and a lot of people will use transfer learning there, so they train a big model and they do like a little layer on top for each of the different tasks, and I'm assuming that it's similar in computer vision. But transfer learning in general, just means taking a pre-trained model and making it better for a specific task. And I'm presuming that they mean for a variety of different data sets. All right. So the problem here is we got so big that we can't fit it into training architecture, like hardware architecture, any more efficiently. So how are we going to continue to get better? The authors are saying it's not going to be by making models bigger, even though that's been sort of an effective thing in the past, because we've gotten, we've hit like sauropods. They're as big as they can get and still be viable. So we need to work on something else, and the thing that we're going to work on is efficiency, so making smaller models work better. Yep. Yeah. Great. Glad that helped us. ConvNet efficiency. Deep convnets are often over-parameterized. Model compression is a common way to reduce model size by trading accuracy for efficiency. So over parameters, like the model's too big, there's too many weights. And so taking a big model and then squishing it down makes it easier to fit on something like a phone. Phones are very small. My husband's a mobile developer, and he's always talking about battery life, which is not something that is even a little bit part of my technical work at all. Because you want to make sure that your apps aren't using all of your phone's battery, and so that they're efficient. Anyway, that's what I know about phones. As mobile phones become ubiquitous, it also becomes common to handcraft efficient mobile-size convnets, such as SqueezeNets, Indola et al. 2016, Golami et al. 2018, MobileNets, Howard et al. 2017, Sands et al. 2018, and ShuffleNets, Zhang et al. 2018, Ma et al. 2018. Recently, neural architecture search has become increasingly popular in designing efficient mobile-sized convnets. Tan et al. 2019, K maybe et al. 2019, and achieves even better efficiency than handcrafted mobile convnets by extensively tuning network width, depth, convolutional kernel types, and that's what Ryan was talking about, the spider eyes analogy that I'm using for my own benefit, and sizes. However, it is unclear how to apply these techniques for larger models that have much larger design space and much more expensive tuning costs. Okay. So we got a small model. We want to find the best model. Previously, people have done that by hand building them, but because they're small, the number of parameters you can mess with is also relatively small, which means that they're really good for neural architecture search because the search space isn't that big, and the neural architecture search has been shown to work really well on these problems, but it's going to be more difficult to do for bigger networks. So what do? This is where this paper enters in. In this paper, we aim to study model efficiency for super large convnets that surpass state-of-the-art accuracy. To achieve this goal, we resort to model scaling. All right, so gotcha. Okay, so the way that they're solving this problem, that small networks are easier to do neural architecture search for because they are small, the search space is smaller, is to do the neural architecture search on a small model and then make the model bigger, which makes the whole process more computationally effective. Okay, so I see how the two parts of the paper are fitting together here now. Robbie says, your husband's also a data scientist. What's his name? No, he's a mobile developer. He does not work in data science. Model scaling. There are many ways to scale a convnet for different resource constraints. ResNet, et al. 2016, can be scaled down, e.g. ResNet 18, or up, e.g. ResNet 200, by adjusting network depth, number of layers. So that's like this guy in the middle here, C, where I'm assuming the number here is the number of layers. That's how I'd name it. Well, wide ResNet, Zagoriko and Komodakis, and MobileNets, Howard et al. 2017, can be scaled by network width, number of channels. It is also well recognized that bigger input image size will help accuracy with the overhead of more flops. So if you have a higher resolution image, you get better results out, but you need to do more calculations because you need to cover the whole image. Although prior studies, Raghu et al. 2017, Lin and... It could be Jagelka. It could be Yailka? I don't know, man. 2018. Sharir and Shashua 2018, Liu et al. 2018, have shown that network depth and width are both important for ConvNet's expressive power. It still remains an important question how to effectively scale a ConvNet to achieve better efficiency and accuracy. So these works are saying, hey, deeper is important, wider is important. They're going to help your model be able to have a more complex decision space. But we don't know how to make them small and still be good. That's the open question. Our work systematically and empirically studies ConvNet scaling for all three dimensions of network width, depth, and resolutions. 3, compound model scaling. Layla says, ignore the names. They're taking 20% of our time. Yeah, but it's the people that have done the work are also important. Also, this is a field that I am new to, so I'm not entirely sure who, like, the major researchers working in the field are. Like, I know a couple of them, but reading the names and then seeing the same names again helps me know, oh, hey, this is a name I've seen before. Doesn't work super well for Han last names because there does tend to be a lot of overlap there. But for more unique last names, if I see them a lot, I'm like, okay, this is somebody whose work maybe I should read in the future because it's being cited in other work that I am reading. I can sort of build my web of knowledge. So. Jem says, I phased out earlier. Was resolution scaling referring to kernel/filter size? I believe it was referring to the resolution of the original image. So I'm probably in pixels, so a bigger image, more pixels. All right, problem formulation. Oh, time to get to the math. A ConvNet layer I can be defined as a function y of I equals fi of xi, where fi is the operator, y is an output tensor, and x is an input tensor. Okay, so we've got our input tensor, we're applying the operator to it, and then we get an output tensor out, and then we can repeat that process. With tensor shape, h, w, c, where h and w are spatial dimensions and c is the channel dimension. So channels are for, like, colors. Yeah. So it's like the old comic books that are printed in 3 colors. Magenta, cyan, and the third one that I definitely know. And so if you were doing it comic book style, you'd have a layer for the magenta and then a matrix that shows which cells have magenta in it, and then one for the cyan, and then one for the third one, and probably one for black. And then those together would give you the tensor for the image, except probably it's going to be more than 3 colors. And people are saying RGB. Okay, helpful. A ConvNet N can be represented by a list of composed layers, and FK. I don't know what this symbol is called, but in IPA, that's the bilabial click. So F. Yeah, if someone could tell me what that's actually called, that would be helpful. That guy, F1, F1 of X, etc., where I know that's not what it is. Circle with a dot. Mois says yellow, magenta, cyan, and yellow. Thank you. I know the pigments and lights are different, and I always get them backwards. J equals 1, K of Fj x1. Convolutional operation or component-wise multiplication. Is this the standard symbol for real? Oh. You can tell how much CNN reading I've done. Not a lot. Okay, so we're doing convolutions on J1 through K, where these are, don't know where we're getting this from. And then, oh, I see. Okay, so this is just a condensed form of this. This is the list of convolutional operations, J through K, that describe the operator function dude, and then they are being applied to our input tensor. Okay, that makes sense. It's just a notation. Frank says star convolution. Star equals convolution. Okay, thank you. Helpful. Star convolution operation. Yeah. In practice, ConvNet layers are often partitioned into multiple stages, and all layers in each stage share the same architecture. For example, ResNet has 5 stages, and all layers in each stage have the same convolutional type, except the first layer performs downsampling. So they get smaller? If they're downsampling, why do they get bigger? I'm assuming there's a very good reason for that, and I'm just not understanding it now at the moment. Okay, therefore, we can define a convnet as, so we do convolutions I through S, for functions, the ith functions, the lth stage. So the stage is the value for each, chunk on top of each other. HCW denotes the shape of the input tensor X of layer I. Figure 2a illustrates a representative convnet where the spatial dimension is gradually shrunk, but the channel, gotcha, but the channel dimension is expanded over layers. That's why it gets bigger. So we are looking at a smaller shape, but we have more things that we can sort it into, and then eventually probably each channel is going to be one of our output classes, would be my guess. And you can do ye olde softmax. Okay, I'm picking up what they're putting down, unless I'm picking up something that they did not put down, and I'm just confused. But I don't think I'm confused. That seems very reasonable to me. The dimension is expanded over layers. For example, from initial input shape 224, 3, so 224 pixels by 224 pixels, 3 channels RGB, to final output shape 7 by 7 by 512, where I'm guessing 512 would be the number of your output classes, and then you have teeny little image. Which also makes sense of how I think of convolutional nets, which is sort of like a little like you're making condensed soup of your soup at every section. I don't know. All right. Unlike regular convnet designs that mostly focus on finding the best layer architecture F, model scaling tries to expand the network length L, length, so being depth, the number of layers that you have, width C, so the number of channels, and or resolution H by W, without changing F predefined in the baseline network. By fixing F, model scaling simplifies the design problem for new resource constraints, but it still remains a large design space to explore different LCHW for each layer. So this is sort of similar to the neural architecture search paper that we read, where the weights were fixed and what was being changed was the architecture of the network, except that what we're doing here is that the weights are being trained, and what we're changing is model scaling F1. Nope, these are the weights. The weights are the same. And what we're changing is the size of the network for the scaling. Sounds right to me. Cool. We'll walk through the math, and I think it'll be a little bit clearer. But it still remains a large design space to explore different LCHW for each layer. In order to further reduce the design space, we restrict that all layers must be scaled uniformly with constant ratio. Our target is to maximize the model accuracy for any given resource constraints, which can be formulated as an optimization problem. And we're still talking about this guy. It looks like it's a composition of function and it's an unconventional notation. Okay, I feel better for not knowing it then. Also, math notation is the source of like 20% of my migraines. It's not actually, math is not a migraine trigger for me. It just is, it can be frustrating. All right, hydration. Okay, so we want to maximize the accuracy of our network given D, W, and R. So these are the only things you were manipulating. And then the accuracy is a composition of all of these, and the things that we're changing are D, which is the layers, so that's what controls the network depth. H and W, which is what controls the network resolution. Okay, I get why they picked these numbers. And then W, which controls the network width, or the number of channels. And these are these are learned, but once learned, they become constants that are applied to the whole network all the way through. Okay. Layla says we are hyperparameter tuning LCH and W parameters. Ryan says we are changing the weight still. We're keeping the ratio of channels and width and depth. Okay, helpful. Where WDR are coefficients for scaling network width, depth, and resolution. FI hat, LI hat, HI hat, WI hat, and CI hat are predefined parameters in the baseline network. So these are going to be coming from the EfficientNet architecture search that they are going to talk about in the future. All right, scaling dimensions. The main difficulty of problem 2 is that the optimal DWR depend on each other, so they're not independent, and the values change under different resource constraints. Due to this difficulty, conventional methods mostly scale convnets on one of these dimensions. Okay, depend on each other. So I think this is sort of the most intuitive with resolution. If your image is bigger, probably also it's going to need more weights associated with it in order to accurately, capture the information that you want it to capture. But they're saying that people generally just do one at a time because it's easier, which, I mean, hashtag overly honest research methods. All right, scooch. Depth D. Scaling network depth is the most common way used by many convnets, He et al., Huang et al., and says Gadi et al. 2015-2016. So this team is probably working on scaling quite a bit. The intuition is that deeper convnets can capture richer and more complex features and generalize well on new tasks. However, deeper networks are also more difficult to train due to the vanishing gradient problem. Z and K, 2016. Although several techniques such as skip connections, et al. 2016, and batch normalizations, Skesdi, same person, 2015, alleviate the training problem, the accuracy gain of very deep networks diminishes. For example, ResNet 1000 has similar accuracy as ResNet 101, even though it has much more layers. Figure 3, middle, shows our empirical study on scaling a baseline model with different depth coefficient D. further suggesting the diminishing accuracy return for very deep convnets. Interesting. I would not have guessed that that's the case. So it looks like as you keep adding layers, you get to the point where adding additional layers doesn't help accuracy. Like, it doesn't make you do the task better, but it does mean that you have to train for longer and that your network is bigger and that it takes longer during inference time. So stop at that point, probably. Are these all going to be discussed in figure 3? Yeah, I'm going to wait to look at figure 3 for a bit. So this is sort of like a whoop, what is that, sort of like square root kind of function where you get to like a flat point, at which point why are you continuing to move along this elbow? Width W. Scaling network width is commonly used for small size models. Howard et al., Sandler et al., Tan et al. As discussed in Z and K, wider networks tend to be able to capture more fine-grained features and are easier to train. However, extremely wide but shallow networks tend to have difficulties in capturing high-level features. Our empirical results on figure 3, left, show that the accuracy quickly saturates when networks become much wider with larger W. Interesting. So deeper nets tend to be able to do more complex things and to be more generalizable. And wider networks tend to be able to capture more fine-grained details, and are easier to train because you don't have the vanishing gradient problem. And then resolution. With higher resolution input images, convnets can potentially capture more fine-grained patterns. Starting from 224 by 224 in early convnets, modern convnets use 299 by 299, this is Gaddi et al. 2016, or 331 by 331, Zoff et al. 2018, for better accuracy. Recently, Gpipe, Huang et al. Achieved state-of-the-art Imagenet accuracy with 480 by 480 resolution. How do they make them bigger? Aren't they a fixed size? Higher resolutions, such as 600 by 600, are also widely used in object detection convnets. He et al. 2017, Lin et al. 2017. Figure 3 right shows the results of scaling network resolutions, where indeed higher resolutions improve accuracy, but the accuracy gain diminishes for very high resolutions. So 1 means 224 by 224, and then 2.5 is 560 by 560. So let's look at these. So this is floating point operations per second. Thank you for the person who chimed in with that earlier. And this is... so this is making the network wider, and we can sort of see it gets better as you get wider, and then it's too wide, and you sort of get diminishing returns. Depth, it gets better as you get deeper, and then it gets too wide, you get diminishing returns. And then resolution, it gets better as you get wider, and then less good, diminishing returns. So all of these features have diminishing returns as you increase the size of the network. I believe we also saw that with the symbolic math paper that we read last time. Off the top of my head, I can't think of examples from this from NLP. At least, again, off the top of my head, the moment I close the video, I'm going to be like, oh, wait, I can think of 3 of them. I think in general, we're still at the point where we haven't reached the ceiling of what bigger models help with in NLP. That may be due to differences between images and language, and that's all that I'll say on that. None says, why is depth kinked? So why is there sort of like a so width has a much smoother curve than depth does? I do not know. I do notice that they are missing 5 and 7. So it could be... Yeah, no idea. No idea. None says, I wonder what the implications are. Again, I don't really know. My guess is that it's just depth is more of sort of like a step function, because it's adding a layer is more work than adding a pixel worth of resolution, or a channel worth of depth. So I'm guessing that they just don't have as many samples, would be my guess. All right. And so what they're saying is that, hey, if you just scale along a single dimension, you're going to reach the point where you reach diminishing returns with that dimension, and it's not going to be helpful to just keep getting bigger, and you're going to run into sort of like, logistical problems with storing and serving and training your model and all of that. Ryan says, have you seen the new Megatron LM from NVIDIA? I have not. I think we have definitely gotten close to the ceiling of NLP in terms of scaling models. That's good to know. I should check it out. Where were we? All right. The above analysis leaves us to the first observation. Observation 1. Scaling up any dimension of network width, depth, or resolution improves accuracy, but the accuracy gain diminishes for bigger models, which I think is a good place to, excuse me, to wrap up the paper, because then they're going to start talking about compound scaling and scaling different things together, which I think is going to be a good next section for us to come back to. So far, the sort of fundamental pieces of this paper, which again is EfficientNet, Rethinking Model Scaling for Convolutional Neural Networks, is you get better results by scaling networks along multiple dimensions at once. Is their claim. We haven't seen the evidence for that yet, but I'm going to assume they're not just lying to us. And that the reason that scaling is very interesting to researchers is, I mean, in addition to just like better accuracy overall, which is nice, is that you can do your neural architecture search and find model parameters, network architectures that might work well for your specific problem on much smaller models, which doesn't take as long, because if I have, 10 parameters, it's easier for me to search a 10-dimensional search space than, a 10,000-dimensional search space. It's just going to be faster and more efficient. So you can find a network architecture that works well for a small network, and then once you have one that works well, you now have a principled way for deciding how to take that small network and make it bigger. And that the bigger network should hopefully have higher accuracy, but also not be as slow when it comes to inference time. So it should be a little bit snappier to put into production, which is nice. All right, so I think that's where we're going to wrap it up now. So far, I'm really glad I made an executive decision. I'm enjoying this paper very much so far. I should maybe brush up on convnets, as we are calling them here, just for my own ease of understanding moving forward. And we will pick back up on next Wednesday. We might, we'll see. We might get, because we're getting to the results, which will probably be pretty quick to read. This might be a 2-week paper. We'll see. But I will definitely be back on Friday at 9 a.m. Pacific time for live coding. And I still don't know what we're going to do. Something. I'm sort of thinking about adding a sentiment analysis component to the forum post summarization project I've been working with, which, by the way, I'm actually using for my day-to-day work now, which is really nice. It's very helpful. It's much, much faster than what I was doing. And I still get to see everybody's beautiful forum posts, which is fantastic for me. And learn what's up with the community. So we'll find out. I'll post about it. Thank you for joining me today, everybody, and I will see you on Kaggle or on the stream on Friday for some live coding. Thanks for joining, and have a great week. Bye!